Okay, great. Thanks, guys, for the invitation. Happy to introduce you to this interesting new topic. And let me share my screen. Okay, hopefully you can see that. And here we go. Okay, so this is a tutorial, and the idea is to present some very simple computations that show the existence of these so-called entanglement islands. And this is based on some work I did last year with Ahmed Almeri, Juan Maldacena, George Santos, and Ying Zhao. And there was earlier and important subsequent work, and many of you would be familiar with these by now by Pennington, Maxfield, Merrill, Fengelhard, and many other people. So I will not try to be, do due diligence to the references. And also I will not try to cover the whole swath of results and their implications. For that, like there have been many previous recorded talks and lectures, especially in the ICTP school and the IAS December workshop last year. Anyway, so before we talk about entanglement islands, we should basically, this talk is going to be about quantum extremal surfaces. And quantum extremal surfaces are surfaces that were introduced by Engelhardt and Wall as a generalization of the Ryu-Takeyanagi surfaces. So, okay, I can shrink this. Okay, so the main thing we want to ask is, how does ADS-CFT compute entanglement entropies or von Neumann entropies? That is one question. And the other question is there some substructure in ADS-CFT? We know that the entire n equals 4 super Yang-Mills is dual to the entire ADS, but can we say that a piece of the n equals 4 super Yang-Mills is dual to a piece of the ADS? So both these questions get answered together. And so I have drawn here ADS3, and the white circle in the middle is the spatial slice of the boundary theory. And B in red is a subregion of the boundary theory. And we want to ask, what's the piece of the bulk which is dual to B? And also, what is the von Neumann entropy of B? The state on B will be mixed because of entanglement with its complement, the rest of the white circle. Okay, and the answer to this question is that you are supposed to pick candidate surfaces A, surfaces called big A in this figure in the bulk. And these capital A candidate surfaces are codimension 2 surfaces in the ADS. Okay, and what are we supposed to do? For each candidate surface A, you're supposed to construct this functional S-gen of A. This is a definition. So for each A, you take the area of A divided by 4g Newton, but you add to it the entropy of bulk matter fields in the hatched region. So this is the hatched region between A and B. And just there's some gravitons, there's maybe some scalar fields in the bulk, all the supergravity fields, they have some entanglement across the surface A. So this is the definition of the generalized entropy functional. Okay, and what's the answer for these two questions that we asked? The claim of Engelhardt and Wall, which generalizes that of Hubini, Rangamani, Ryu, and Takenagi, and FLM, is that you're supposed to take this generalized entropy functional as a function of A and just minimize it over all A. And the minimal answer is the entanglement entropy of the region B on the boundary. So remember, B was this red region on the boundary, okay? And the minimizing surface, A star, is called the quantum extremal surface for B. Okay, and then further naturally, the claim also is that the gravity subregion dual to B is the region between A star and B. Okay, so what this says is that once you found the correct A star, the minimizing one, this hatch region, is the subregion of ADS that's dual to B. Okay, so that's the claim. That's the setup. That's what we are trying to compute. So we are going to just have some setups with some gravity theory coupled to some matter and try to compute these A stars for various setups. Okay, just two remarks that this S-gen quantity is UV finite. because it was understood long ago that even though S bulk is one loop exact, sorry, it has one loop divergences, those one loop divergences are precisely the ones needed to renormalize G Newton at one loop. I think basic pieces of the story understood. I'm not sure if it's 100% understood, but we will assume that this S-gen functional has UV divergences that cancel in this way. And also in the bulk, graviton contributions are not very well understood. So since we have ADS, there, if in higher dimension, there would be graviton fluctuations, and we don't understand that. So to evade that, we take the bulk matter to have a large number of degrees of freedom. That means that the bulk would be some kind of QFT, which has a number of degrees of freedom much bigger than one, but much less than n squared, where n squared sets the G Newton in the bulk. Okay, so you should imagine, let's say you have 1,000 scalar fields in ADS4. So you just have like 2 gravitons, but you have like 1,000 scalar fields. And so their contribution to S bulk will be the dominant one. And then we don't have to worry about the gravitons. Okay, so are there any questions at this point? Okay, great. But we know, like, if you're in ADS4 or something, like, computing S bulk is impossible. It's just like a nightmare to compute entropy even of a free scalar field in 4 dimensions. And okay, so what do we do? Like, you might say, okay, you set up this proposal, it's basically useless. You can throw it out of the window. Like, at least with Ryu Takenagi, we could compute surfaces and we could make some progress. Okay, so there is a scenario in which we can compute these, and it's when the gravity theory is 2-dimensional. So we have ADS2, and maybe that has some CFT1 dual. And because the bulk matter we can take to be a conformal field theory, a 2-dimensional conformal field theory, and Calabresi and Cardi and many other people have given us formulas for the entanglement entropy of subregions in a 2-dimensional CFT. And this actually was already used in a very prescient paper in 1994 by Fiola, Preskill, Strominger, and Trivedi, in which, in the context of the CGHS model, they were computing entanglement entropies of Hawking radiation using the Cardi-Calabresi formulas. And also the paper by Almheri, Engelhardt, Merolf, and Maxfield from this May use this. And the second scenario, which I will not describe, will be described in Dominik's talk. So I will skip this. So this is what we're going to do. Okay, so now I'm going to give you 2 examples from this paper that I wrote with Ahmed and Juan. Okay, and so here's the setup. The setup of this paper is that we have this so-called very simple theory of gravity called the ADS2 JT gravity. And it has 2 dynamical fields. There's a scalar phi, we'll call it the dilaton, and the metric G. The action, the main part of the action is here. It's phi times r plus 2. It's not just usual Einstein action because in 2D it's topological. So that's the action. It's just phi times r plus 2. And there's a Gibbons-Hawking boundary term. What I want you to focus on is this constant phi r here. So this phi r has dimensions of length because this epsilon is some kind of holographic renormalization parameter. It's where we put the cutoff in ADS. And epsilon has dimensions of length, and phi r also has dimensions of length. And this will play a role when we try to solve for surfaces. Phi r will be the quantity setting the scales of various things. Okay, and G Newton in 2 dimensions is dimensionless. So what's so nice about this theory is when you make the functional variation with respect to phi to find the equations of motion, you get r plus 2 equals 0. So it says that we have a constant negative curvature space-time. And that's good because in 2 dimensions, locally, it's enough to fix the form of the metric. Like it just has to be ADS2 or in Lorentzian and hyperbolic space in Euclidean signature. Okay, but so that's like the local stuff. We know that it has to be some ADS2 space, but I should say there's also equations coming from the metric, like ddg mu nu, and that imposes some conditions like grad nu phi plus g mu nu grad squared phi equals 0 in this case. So there is some also some equation of motion that the phi has to satisfy. Okay. Okay, so the boundary conditions are we impose a Dirichlet boundary condition on the metric. So we have some ADS space. It has a time-like boundary. The TT component of the metric has to be big, like because the boundary gets big as we go to ADS. And the dilaton also has to be big. It has to be this phi r over epsilon, has to be the value of the dilaton at the boundary. Okay, so before we launch into it, I should say that we are in gravity in 2 dimensions. So codimension 2 surface is just a point. So our candidate A surfaces are just some set of points. It's just 1 point or maybe 2 points or a set of points. So what do we mean by the area of that surface? And what it means, the area of a point A, it just means the value of this phi field at the point A. That you can see because it's phi, which is multiplying the 2-dimensional Ricci scalar here. And yeah, and one way to also think of this phi is if you got this theory from dimensionally reducing a theory in ADS3, then phi would just be the length of the extra circle. So that would be like the area of the horizon in a 3-dimensional gravity. Okay, so that's what we have to remember, that phi of A, it plays the role of the area. Okay, and we will often set 4g Newton equals 1. So that's a dimensionless, we'll forget about the g Newton. Okay, so now we need to we have a Lagrangian, we have the boundary conditions. We need to write down a solution of our classical dynamical system. And here's a solution. The metric is just Poincare, ADS2 metric in Lorentzian signature. And I will take x negative for reasons that will become clear later. And I've also defined here x plus and x minus, which are the light cone coordinates, okay? And if you solve now the equation of motion that you get by varying the metric, that gives an equation for the dilaton, you will see that the dilaton should be this phi r constant divided by negative x. It's positive because x is negative, okay? And phi itself is dimensionless. So here again, you see the dimensions work out. And the boundary conditions will be satisfied if we put the boundary at x equals negative epsilon, right? The TT component of the metric would be 1 over epsilon squared, and the dilaton at the boundary would be phi r over epsilon. Okay, so here is the picture. Here's ADS2. I've drawn the origin, the x and the t directions, and the green line is the boundary cutoff. It's x equals negative epsilon. This is the locus x equals negative epsilon. And you have to imagine that there's a dual system to this ADS2, which is just some quantum mechanics. It's just maybe some bunch of fermions, if you like, some SYK fermion, some quantum dot, and it's just evolving in time. Okay, that's the dual. The precise dual will not be important, but it's important to have it at the back of your mind that we have this quantum mechanical dual. Okay, because strictly speaking, I will define all the entropies in the quantum mechanical system. So all subregions and all entropies would be defined in this, and we would compute it using the holographic dictionary. Okay, so now we need some matter, right? We had in the generalized entropy, we didn't just have the gravitational system, we also have some matter. So there's this chi field. Chi is a matter field. And now the total action for phi, g, and chi is the JT action plus the CFT action. And we take the matter field chi to couple only to the metric. It's just a choice. It doesn't couple to the dilaton. Okay, and okay, so that's it. We have our space-time. It's like some 0 temperature state of some system, and I've told you everything. And now we just need to quickly review some entanglement entropy formulas in CFT2, and we'll be good to go. We'll be able to get to the quantum extremal circuit. Okay, are there any questions about this stuff?
May I ask a question?
Yes, please.
Why is there this choice of coupling the CFT only to the metric and not to the dilaton? Does coupling to the dilaton make calculations particularly difficult?
Yeah, it makes life hard and it's not necessary. So we are able to get all the qualitative lessons from just this model. So, and it will couple, like if you imagine the JT gravity coming from some dimensional reduction, and it's like the near horizon region of some long throat, the transverse sphere is approximately constant in area along the throat. It varies slowly. So that's why it's okay to neglect it to leading to some kind of approximation.
Thank you.
Yeah.
Can I ask another question?
Yes, please.
So I have a question about the general point you said in the beginning that you take the matter fields to have a large number of degrees of freedom, so you don't have to worry about the graviton contribution.
Yeah.
Would you say, like, what kind of complications will arise? So let's say if I go away from the toy model and I do want to have actual gravitons.
Well, I don't want to address that question right now because it's maybe not like, it's not necessary for the talk. So it's just like how you split the matter contribution between the area, because the graviton also affect the area.
Right.
Right. So that's the tension, but it's not like the subject of this talk. So I apologize. I'm going to evade that question for now.
Thanks.
Question here.
Yeah.
So you want to compute this entropy with the matter field contributions in the bulk taken into account. The difference between this Engelhardt-Wall formula and the standard Ryu-Takayanagi formula is that here we are trying to compute a fine-grained entropy as opposed to a coarse-grained entropy, or is there something else?
No, they are both fine-grained entropies. It's just a different level of approximation. So if you delete S bulk from the Engelhardt-Wall formula, if you delete the second term, you get back precisely Ryu-Takayanagi formula.
Correct. So, but what was the need? Like, sorry, can you clarify what was the need to add this additional term?
Well, you can think back to Bekenstein, right? So as black holes evaporate, the area shrinks. But what is the thing we need to add in order to have a second law of thermodynamics? It's precisely the entropy of bulk fields outside the black hole. So that's just the original motivation of constructing this quantity, that it's the quantity which, even when black holes evaporate, continues to increase in that context. So then it's natural to consider this quantity. And we'll see it has a nice trade-off between the area term and the entropy piece. Yeah.
Okay. Thank you.
Hello?
Okay, so let's, yeah.
That's just a comment. So it doesn't feel like the dileton is playing a very important role, right? I mean, these things like area and all are well defined in higher dimensional spacetimes as well. So I do not understand why dileton fields are particularly necessary. Can you say it again?
If you didn't have a dileton in a two-dimensional gravity, the action you would write down is just the Ricci scalar, right? Like the Einstein action.
Yeah, right, yeah.
If you derive the equation of motion corresponding to that, that's an identity for all two-dimensional metrics. It's not an equation, it's an identity.
Right, okay.
So it's just trivially zero. So it doesn't give you any dynamics. So you need to have this phi field. And phi and g, you should together think of it as the gravitational variables.
Oh, okay, thank you.
Okay. All right, let's go on. So, okay, just a quick fire review, since it's a tutorial of entanglement entropy formulas in a CFT2. The entropies are defined for space-like line segments. So here I have drawn a space-like line segment AB. And if it was perfectly straight on a time slice, its entropy would be C/3 log L divided by epsilon UV, where epsilon UV is some UV cutoff. This is the famous Cardy-Calabrese result. C is the central charge of the 2D CFT. I'm going to just write it slightly differently as C/6 log of L squared. And the L squared gets generalized to the Lorentz invariant interval because the interval was not straight, it's tilted. So it has some time separation as well. And X plus and X minus are the light cone coordinates. So we get a C/6 and we get a delta X plus and a delta X minus. So we get some contributions from the right movers and some contribution from the left movers. Okay, so that would be in flat space. But there's a twist because we are interested in CFTs propagating on curved spaces. And because you have a non-trivial metric, the UV cutoff needs to know about the metric. Like we need to put cutoffs in terms of the proper distance, not some coordinate distance. And that introduces these factors of some additive terms of negative C/6 log omega at A and negative C/6 log omega at B. What's omega? Omega is the Weil factor in the metric. So we will always write our 2D metrics in conformal gauge, in which we have something that looks like a flat metric times an overall function, omega of space-time. And omega of A just means the function omega evaluated at the point A. And that comes, you can see that in two ways. One is that the cutoff needs to know about omega, or if you think of the entanglement entropy as being computed by correlation functions of some twist operators, because the twist operators have a scaling dimension, they know about the Weil factor of the space. So that comes in either way you think about it. And all these ingredients will be very important. Okay, so now let's go ahead and compute an entanglement wedge. Let's just compute an entanglement wedge. We have a CFT1, it's a quantum mechanics. So the boundary is just a single spatial point, right? There is no substructure, there is no B or anything, it's just a point. So we can just compute the entanglement wedge of the entire boundary, which is just a single point. And we had better find that the entanglement wedge is the entire Poincare patch, right? Because all of the CFT has to be dual to all of the ADS. Otherwise, we have done something wrong. Okay, but one last thing we have to remember is that the ADS2 space has a boundary. It has a boundary at x equals 0. So we actually have a CFT on a half space. And on a half space, these log delta x plus and log delta x minus contributions do not contribute separately, right? Because there is some reflecting boundary condition at the half space boundary. And so the left movers get identified with the right movers. And we will just get one of the light cone contributions to the von Neumann entropy. Just be some C/6 log of one of the coordinates. Okay, so here I have drawn the picture. Our point B is the system whose entropy and entanglement wedge we are trying to compute. A is the candidate point. It's a codimension 2 surface, just a point. And AB, the green line segment, is the hatched region that I drew before. So, okay, we are supposed to compute the generalized entropy functional. So I was going to fill this in here. Let's assume that the x coordinate of the point A is x. Okay, so B is at the origin and A is at x. So S gen of x is the dileton. So the dileton is phi r over negative x. That was just the solution, right? Plus I have C/6 log of delta x plus. What is log of delta x plus? Here I have written the x plus x minus coordinates is just negative x, right? The first coordinate. And we don't get a contribution from x minus. But there is a contribution from log of omega at the point A, right? I don't need to write omega of B because that's the point we are not varying. So I just need to extremize this with respect to x. So what is omega of A? Let's remember that our metric is just negative dt square plus dx square over x square. So omega is just negative x, right? Okay, so I'm going to write here negative x, okay? And well, we see that these two terms just canceled. Okay, so the generalized entropy functional is basically just phi r over negative x here, plus maybe some constants. So, okay, where is this extremized? It's extremized at x equals minus infinity, right? That's very simple. And so here we get our A star. A star is all the way to the Poincare horizon. So the entanglement wedge of B, is this entire Cauchy slice. Okay, so good. We've recovered this obvious fact. So it gives us some, I don't know, some kind of warm-up exercise to this, working with these generalized entropy functionals. Okay, so are there questions at this point about this, just about this setup?
Yeah, I had a question.
Yeah.
So the question was, so here, why don't you put the boundary at epsilon? Initially, you had the boundary at some epsilon, right?
Oh yeah. You can put that's not going to change the results. Right? You can put it at epsilon. Yeah.
That won't
That's
change
fine.
the result.
No, because we are varying A, right? A is in the bulk somewhere. The point A is somewhere in the bulk. So even if you move B a little bit inwards, I mean, there would be some epsilons in this x plus epsilon, but you know, x is order 1 and epsilon is small, so it is not going to change the results. Like, you're saying that I should put B here as epsilon comma minus epsilon. So
Yeah.
and then in the end, the epsilon is taken to 0 anyway, so it doesn't matter.
Oh, okay. Thank you.
Good question. Okay. All right, so now to make things more interesting, I mean, here we had just some quantum mechanics. We didn't have any substructure. So what are we going to do? We are going to take our quantum dot of SYK fermions, and we're going to couple it to a wire. So a wire you should just think of as some made up of some spins or something that has some CFT2 living on it, and it's a boundary. It has a boundary, and at the boundary we couple it to this quantum dot that was a holographic system. And what's the motivation for this setup? The original motivation comes from making a large black hole in ADS evaporate. So we know if we were in ADS5 or something, big black holes, which are stable thermal equilibrium states, don't evaporate. And to make it evaporate, you imagine on the dual quantum mechanical side, taking the n equals 4 super Yang mills and just coupling it to a heat bath. So you have some hot, super Yang mills at finite temperature, and this heat bath just takes away heat from the n equals 4 super Yang mills. So that's like causes the system to lose energy, cool down, and the black hole sort of disappears from the bulb. So that's the motivation, but we are going to here use it in a two-dimensional setup. And it plays the same role. It tries to make the black hole evaporate and so on. But here we are not going to be in that situation, but that's the motivation for why we join in this wire, like why we construct this hybrid system, like some 0-dimensional plus 1-dimensional spatial system. Okay, and here's a natural guess for the gravity dual of the system. And I should warn you that this is not as rigorous as the original ADS5 CFT correspondence, but here it is. So on the dual side, we have this SYK fermions coupled to a wire, right? And we just imagine that the SYK nucleates the ADS space. So from here on, or the green line on, the SYK disappears, nucleates the ADS space, and we are left with some ADS space joined to flat space. So to the left of the green line, we have some ADS space. And on the left, we have just some flat space. So the green line acts as some kind of domain wall between an ADS space and flat space. And also the gravity is not dynamical in flat space. So here, G mu nu is not a variable. It's not something you would vary or you would integrate over in the functional integral. On the left-hand side, it is. Okay, that's just because this wire had some CFT living on it. And yeah, okay. So that's the candidate dual, and there is support for this going back to the works of Randall Sundram and work done around that, but we'll just assume it for this talk and for all the works that have been done in the doubly so-called whatever, all this stuff assumes this duality anyway. Okay, and just to make our life simple, we take the wire to be made from the same CFT2 that was propagating on the left on the ADS2 side, okay? So what's going to happen is that the fields in ADS that were earlier bouncing back like that, right, had reflecting boundary conditions. Now we can supply them transparent boundary conditions. They can just go through. A field from the right can come into the left, and a field from the left can go into the right. That's the difference from the previous setup. Okay, so we will get these two separate contributions from delta x plus and delta x minus now in the Cardi-Calabrese formula. Okay. All right, so now let's see if something happened to the entanglement wedge of just the point O, right? So we have this thing, O is this origin, and to consider our system to be just the original holographic system without the wire, okay? So this has some entanglement entropy with the wire because we are imagining that the coupled system is in a T equal to 0 ground state. So these fermions plus the wire are in a joint ground state and they're interacting. So the fermions themselves must have some entanglement entropy. Okay, so let's see. So we have the dileton term as before. That didn't change. It's just phi r over negative x. And this here was log of delta x plus, okay? And delta x plus is the same as delta x minus. So that's why we get now this factor of 2. Right? We have transparent boundary conditions. It's not a boundary CFT anymore. So we get this factor of 2. And we still have this correction coming from the Weil factor. And I remind you that omega of A was just negative x. So the 2 minus 1 gives you 1. And now you get a more interesting generalized entropy functional as a function of x. We have phi r over negative x plus c over 6 log of minus x. And all of us can take its derivative very easily. It's 1 over x squared plus 1 over x. And it's extremized at some negative x, right? We set it to 0, we get x equals negative phi r 6 over c. So we see here that phi r is setting the length scale of where this quantum extremal point is, a star. So a star has an x coordinate, which is negative phi r 6 over c. Okay, so now let's see what this means. So we were computing the entropy of this piece, right, of the system, which is just this SYK dot or fermions, whatever. And we found that this quantum extremal surface is at some finite location. It's not all the way at the Poincare horizon. It's somewhere here. Okay, so what this means is that the entanglement wedge is now just smaller. Earlier, it was the entire Poincare patch. And now the entanglement wedge of just this SYK dot, which you might have thought is nucleating the entire ADS space, right? Because that was the system which was holographic, is actually smaller than the Poincare ADS. It's just somewhere here. And this is the entanglement wedge. Okay, so the moral of the story is that once you couple your holographic system to a wire, it no longer sort of is responsible for creating all of the ADS space. It only sort of is dual to the space between A star and B and the diamond on top of it. Okay, all right. That's just one statement. And let me just say, why is this weird? This maybe doesn't sound so weird at first place, because, okay, you coupled in a wire, you changed the system. So why are you surprised that the entanglement wedge changed? Okay, from this point of view, it's not very surprising. But the surprise comes when you look at the entanglement wedge of the complement system. So the complement system is just some wire on this side. It's just some CFT, right? And if we were naive, we would think that its entanglement wedge is just this causal diamond, right? We would think that the entanglement wedge is just responsible for just its own, like, causal wedge. So this is the sort of the causal wedge of the wire. But we know that the full system on the boundary is responsible for creating the full space in the gravity picture. So it must be that this blue region in the CFT side is creating not just this part of the space, but also this part of the space, right? So because the region between A star and B was dual to the SYK dot. So this is the weird thing. It tells you that the entanglement wedge of this blue wire is disconnected. There's a naive region, which you thought, okay, it's the causal wedge, but it has a disconnected piece deep in the gravity region near the Poincare horizon. And this is the thing here that's called the entanglement island, this region between the Poincare horizon and A star. So the words we use are that the entanglement wedge of the wire contains the region B to infinity union H to A star. And this H to A star region is the island, is the entanglement island. So we have our first, just a very, very simple computation. I mean, look, it just came from extremizing this function, but the conceptual, inputs are very important in understanding this. So let me just say, so this is kind of bizarre. You might think that there's some non-local effects operating, and it's just that the entanglement wedge of a region you thought that is non-gravitating contains a region very far from itself, close to the Poincare horizon. Okay, and let me pause for questions here, because I think I have made my point, and this was the only sort of thing I wanted to start you guys off with, and the rest is just sort of add-on. So let's pause here for questions.
Hi, Raghu. Go ahead.
Okay, I have a question. I thought that the Ryutakanagi prescription is only valid for static spacetimes, right?
Well, there's the HRT thing, which is also valid for time-dependent things.
Yes, but in this case, isn't the setup that we have like an evaporating black hole?
No. So that's why I said that was the motivation. So you see here, the setup is just a 0 temperature ground state. All right, it's just empty ADS coupled to vacuum on the bath side. There is no evaporation. There's not even a finite temperature. It's zero temperature
Right.
ground state.
So in the case of the finite temperature, we should use the HRT prescription instead of Ryuta-Kanayagi, is that right?
That's right, if you have an
Okay.
evaporating black hole, but it's sort of, I mean, they're morally the same. They're not that different, like all these prescriptions. It's just some, again, some minimal area. Maybe you have to do some mini max and things like that, but
Okay.
it's not qualitatively different, I would say.
All right.
Mhm.
So, I have a question.
Yeah.
So in the generalized entropy, the central
Yeah.
charge which is appearing is the central charge of the CFT living on the ADS2.
Yes, exactly. Yeah.
So how does the entanglement entropy know about the system to which my quantum mechanics is coupled? Where is the information of this CFT on the wire coming in? Or does
Oh,
it-
it's coming in the boundary conditions. Good question. So we have this B locus here, right? Sorry, not the B, this green line here, right?
Yes.
And we have these two spaces kind of joined together.
Mhm.
And it's important that the fields from this side can propagate here, and the fields from this side can propagate here. So there is some coupling between these two spaces, or in the dual picture, there is some coupling between the SYK and the CFT. If there was no coupling, these two spaces would just be two different universes, not talking to each other.
Yes. So, but can I see those boundary conditions playing a role in the entropy that you just computed? Because they're
Yes, yes. So you see earlier when we didn't have the wire, we didn't have this factor of 2,
yeah. Okay.
right?
Okay.
So that's what changed. We got these two terms didn't cancel anymore.
Yeah.
That
Okay.
was the difference.
Okay. Thank you.
Okay.
Hey Raghu, can I ask a question?
Yes. Yeah.
So I have a problem calling this entanglement wedge because I thought that the entanglement wedge is enclosed between the quantum extremal surface and the region in the boundary that we are interested to compute the entropy of. But now
Yes.
it seems that you're using the term kind of in a different context, or what's going on here?
Yeah, good. Very good. So this was actually exactly the confusion after the papers in May. So these guys found that the entanglement wedge of this SYK, the analog of this SYK fermion is between A star and B, right? And then initially, in the AEMM paper, there's even a paragraph, okay, it looks confusing because you might think that the entanglement wedge of this blue region is basically this B to infinity region. And then you're kind of confused what this H to A star region is. And actually that's where these doubly holographic setups come in very useful. So as you will see in Dominik's talk, is that it's very pictorial. So you should think, okay, let me just say one more, since you asked the question, how does the homology constraint is satisfied, right? That's what you're asking. How is the homology constraint satisfied? So imagine now that the CFT that's living on this diamond here, the C is also big. So C is very large and it's itself holographic.
Okay.
So you have a third dimension ADS3 coming out of the board. Okay. So you have deleted the CFT degrees of freedom and added a third dimension.
Okay.
What happens is that in the third dimension, this causal diamond, the blue sort of region, it starts there on the plane of the picture, starts to come out into the ADS3 direction. Okay.
Okay.
It turns over to the left and then
Right.
attaches to the H and A star region. Okay.
Okay.
So
I
it's
I've seen those kind of pictures. Okay. So
yeah.
You're saying
And
without double holography, we cannot explain this?
Well, you can infer it like, back there, because the way to think about the homology constraint in this setup is that this gravity region is like, yeah, it's more clear in this doubly holographic setup, I would say, like the homology constraint, because a Ryuta-Kanayagi surface that can end on this Randall-Sundrum brane is homologous to the original region on the the actual dual system. So that's why it's conceptually important to have also have had this doubly holographic system.
I see. Great, thanks.
Yeah. But it's weird. Yeah. I want to emphasize along those lines that this is a signal of some kind of non-locality. in the gravity theory, and it's okay. Like we know that quantum gravity has some non-local elements, yeah, so it's okay. But I say that with a lot of caveat. I mean, there is still some causality conditions that are obeyed if you think of just the boundary, but it's just there is something weird, like there's something non-local, and I can say more about that. Yeah, but there was another question.
Yeah, hi. So there is this
Yes.
theorem which says that the causal wedge should always lie inside the entanglement wedge, right? So in the
Yeah.
previous diagram, when the quantum extremal surface comes out, it doesn't seem that that theorem is being obeyed. Is there? I mean, in the
Sorry.
previous diagram to what you have
In
shown.
here?
Yeah, in that one. Yeah. In that, is it that the causal wedge lies outside the entanglement? It encloses
Sorry,
the entanglement wedge.
It's the cause. I mean, it's just a point, right? So if you just think of B, it's just a quantum mechanics. So there is no wedges in just a 1D system, right? It's just a point,
Okay.
like the causal wedge on the boundary is just a point.
Right. No, I mean the causal wedge in the bulk. Wouldn't that be the right triangle, the whole thing? No.
No.
Because B is the entire boundary, right? So the causal wedge is like the entire space-time.
No, that's the thing, right? The entire dual is this B union the wire. B is no more the entire spatial system.
I see. Okay.
Right. It's B plus this is B here, or whatever you want to call it, plus this whole stuff, right?
Right. Okay. Fine.
And here you see that it is true that the entanglement wedge is bigger than the causal wedge, because the causal wedge is just the blue diamond on the right, and you have an extra piece on the left. So the entanglement wedge is bigger than the causal wedge.
Yeah. Right. Okay. Fine. Okay. Thank you.
Okay.
All right. So there's a question in the chat that I thought I'd just read out.
Yeah, sure.
So this is from George Holsey. Should it be clear that when we take the complement of the CFT system, we should consider the complement of the entanglement wedge also?
Right. So I would answer this that initially you might have been skeptical because this faraway region seems so bizarre. But I think this doubly holographic setup sort of eliminates all doubts that that this is the correct picture. So, I mean, you may not want to assume the complementary recovery thing on this 2D picture, but if you add in this third direction, it becomes clear that you can derive this complementary thing, that the entanglement wedge of the complement is equal to the complement of the entanglement wedge.
Hi, can I ask a question?
Yeah.
So I'm just wondering about the degrees of freedom inside the island. Like, can we still consider them part of the ADS spacetime?
Okay, yeah, good question. So actually, I was going to comment on this when I said that. So let me erase some of the stuff. This picture has become a bit messy. Okay. So what do we want, right? So part of the entanglement wedge story is that there is entanglement wedge reconstruction, right? What this means is that if I have an excitation in the bulk region, in this hatch region, then I can sort of write an equivalent operator on the boundary theory, which sort of acts the same way on all states or on enough of the states, right? So let's say I create an excitation here. Oh, sorry. So let's say I create this pink excitation here in this bulk picture. Okay. You can ask, since the entanglement wedge, this lies in the entanglement wedge of this wire here, this excitation should live in this blue system, right? So it'll correspond to some simpler thing. Maybe it has to be decorated a little bit, but it'll correspond to some excitation there, which looks more or less like this one in the bulk, right? That's like saying that the causal wedge reconstruction is not that dramatic. It's just some causal wedge reconstruction. Okay, but imagine now you have some excitation here in this island, right? Now you will need to use this more fancier versions of entanglement wedge reconstruction, like this PETS map or the modular flow. And this simple excitation in the bulk will correspond to some horribly non-local thing in this wire, but it will still be confined to the wire. It won't go into this SYK system, right? So that's the difference. Like the piece of the entanglement wedge that lies behind the causal wedge has more complicated operator reconstructions. So that's how it interplays with that. That just simple excitations here become very complicated, sort of modular float operators in the dual system. Does that answer the question, or?
Yes. Thank you.
Okay.
Hey, Raghu, I have another question.
Yeah.
So if is it necessary that the CFT for the reservoir has a 0 temperature, or it can be a thermal CFT?
Well, that was going to be my next set of things. If we get to it, I can discuss the finite temperature story also.
Okay. Hope you can.
But you can do it. It's just the formulas become more complicated. You get some cinch of betas and stuff like that, but more or less it's the same.
Okay, thank you.
Okay, let me go on to the finite temperature case. Let me skip this generalization. I was going to describe this generalization where you don't just compute the entropy of the SYK dot, but you include a little bit of the wire. So then you're computing the entanglement wedge of this system and its complement. And there is some nice consistency checks you can do, but okay, that's let's accept that this will also have some entanglement wedge. The formula for X star, A star will be a little bit more complicated. The story is more or less the same. Okay, so now let's come to non-zero temperatures. So here we want to imagine, you have this SYK system plus its heat bath, and we want to put them together in a thermal equilibrium at inverse temperature beta. Okay, but we can purify the system, introduce its partner, this thermophile double, and have the partner SYK and the partner wire on this side. So this will be our setup. We'll have two SYKs, each coupled to their heat bath, and the density matrix of the right SYK plus the right wire is a thermal density matrix of the joint system. They're still interacting and so on and so forth. Okay, we have here this ADS space, ADS2 space. It's these white things. The yellow is the original Poincare patch, but we know that when we think of a finite temperature solution, we are supposed to think of the Rindler patch in ADS. So these white lines define the Rindler patch. And I will say, just changing a patch, you might think you just change the coordinates. So what does it matter? But there is something that does change about the solution, which is the dilaton. Okay, but we still have this ADS coupled to flat space. So we have here flat space on the right and a flat space on the left. So sort of this kind of thing is going to be our interesting things, and we can complete it into the full patch if we want, and so on and so forth. So this is the arena. Okay, so now I have to tell you the relevant JT solution. It's no longer the old solution, it's a different solution. Well, the metric is locally the same, right? As we said, all solutions to the metric are just locally ADS2. And here I have just transformed from the Poincare coordinates to some other y plus y minus coordinates, where y plus is like tanh of x plus, and y minus is a similar formula in terms of x minus. Okay, so this is just a coordinate transformation. There's nothing going on there. Point, of course, is that y plus only covers a finite range in x plus. Okay, so what is really different about the t equals 0 solution is the Diletton profile. So earlier we just had this piece outside. We just had a phi r over x, right? X minus minus x plus is just the spatial x. Now we add in a term here. We add in a term proportional to the temperature. So when temperature is 0, this term will not be there. And this is what's different about the finite temperature solution. And this affects the boundary conditions. It affects like where the singularities are and so on and so forth. Right. So I want to just emphasize that viewpoint. Okay, so now again, we just want to play the same game. We want to construct the quantum extremal surface condition for, let's say, this right SYK plus a little bit of the wire. Okay. And you basically get some condition. Okay, so I have written here for you the condition on this A star. This is an equation which you can solve for A star. There are these cinches proliferating everywhere because the matter CFT that's moving on the ADS spacetime is at finite temperature. And the Cardy-Calabrese formulas at finite temperatures have these cinches in them. Okay, so that's why there is a cinch all over the place. There is still a phi r, which is setting the scale, which would set the scale of A star, and so on. Okay, so the same thing sort of goes through. Okay, but I want to get to the setup where we see this page curve. Okay, so we have some finite temperature island, blah blah. It's the same story as the zero temperature system, but where will we see the first instance of the page curve? Like why is this important? Okay, so consider instead the system which I drew here. So the left wire up to this point and union its partner on the right. So the right wire on B. Okay, and these are in some thermofield double state, and like imagine running time forwards on both sides. So for those of you who are familiar, this is basically the Hartmann-Maldacena setup of modeling a quenched state and time-dependent entanglement entropies. So we have this left union right system, and if we evolve them forwards and backwards, it would be an isometry and the entropy wouldn't change. But we are evolving them both forwards in time, okay? And that leads to time dependence and basically leads to a linearly growing entropy. And you can compute it. I was going through the computation here, but it's maybe not important, the derivation. But the point to note is that if you compute the entropy, S of t, S of time, you will find a log of cosh of t, okay? And at times, which are just a few times beta, this is linear in time, right? The cosh becomes just an exponential and you get a linear in time growth. So this entropy is growing linearly, okay? You can say, okay, fine, it's growing linearly, it can go on forever. But again, think about the complement system. What is the complement system? The complement of these two wires is just the two SYKs, right? And the SYK, being a fermionic system, has a finite number of states. So it has an entropy which is bounded by 2 times the Bekenstein-Hawking entropy. Like if you had some, the infinite temperature state in SYK, whatever, it would have some entropy, finite entropy. So okay, so it can't grow linearly forever. Like this answer we got has to be just wrong at late times, and something has to come in and save the day. Okay. So what happens is the following picture becomes. So at late times, again, the entanglement wedge is bigger than the causal wedge. So the causal wedge would just be this right wedge union this left wedge. Plus you get this island. So this would be the island here in this case. And so now you're supposed to compute the entropy of these 3 systems together. And that answer is independent of time, as you can see the computations in our paper. Okay, so that entanglement is independent of time. And so you have the following computation. So you have a quantum extremal surface, which is just the naive one, just the causal wedge, in which you have this linear growth of entropy, basically because of Hartmann-Maldacena type effect, where the TFD state is not a ground state of the Hamiltonian. It's just some excited state. And when any excited state undergoes time dependent, undergoes time evolution, its entropy grows linearly in time. And then we have this late time saddle which comes in. So the entropy follows this linearly growing, then gets cut off by this other non-trivial island surface and becomes flat, saturates at 2 times the Bekenstein. And the time of transition is basically temperature times the entropy, which is of the same order as the page time. So this is a toy model of the page curve. The actual page curve, of course, you have some linearly growing, you have something going down, but that's for an evaporating black hole. This setup was a finite temperature black hole in thermal equilibrium with a heat bath. And this is what the page curve sort of looks like in this case. Okay. All right.
Can I just ask a question?
Yes, please.
When you say the black hole in a thermal equilibrium with the bath, do you mean that both systems are in a thermal state at a given temperature, or only that they have equal temperature?
No, I mean that the state, if you were in a lab and you had no gravity, you just had some quantum systems, you would take your SYK fermions, you would bring in the wire, and you would try to bring these two systems together, the coupled Hamiltonian, to the state e to the minus beta h total.
Okay, I see.
That's the state.
But then why would the entropy increase if you have a system like this, when the evolution Hamiltonian is unitary?
Well, that's why it's important in the Hartmann-Maldacena setup to consider not just this system, but a thermophile partner. And it was also important that the system we are considering has support both on this side and on this side. Right? So it's not just the piece of the wire on the right-hand side. It's the right-hand side plus its thermophile partner undergoing this sort of quench evil. Okay, let me just say for people who might not be familiar, I'm keeping mentioning. Okay, so the thermophile double state, okay, is e to the minus beta en over 2, n left, n right, right? Sum over n. So it's just some entangled state whose entanglement entropy of the left system is equal to the thermal entropy. Okay, h left minus h right annihilates the thermophile double, right? It's clear because we just get en minus en in each term. So this is 0. So what this means is that exponential of it times h left minus h right on the thermophile double is equal to the thermophile double, right? But this is not the time evolution we're doing. We are thinking of this, right? Just if you have two systems, the natural time evolution to consider just h left plus h right. And this is not 0. And so this is not equal to it. So this state here is a rapidly time evolving state. It's just like you had a spin system. It had some interacting Hamiltonian, but you froze the spins to like all up, spins all up. So that's some very highly excited state. It has it has small entanglement. But then when it evolves, this entropy almost rapidly grows linearly, like from this quasi-particle picture of Cardi and Calabrese again. So this is the underlying sort of mechanism that the thermophile double state on the Hamiltonian acting on the thermophile double state is just some generic, this has some high energy.
Okay,
so it's important to have the left system and the right system and consider these two things together, right? Okay. Does that answer the question or?
Yeah, that's perfect.
Okay.
Thank you.
Okay, thanks. All right. Yeah.
All right. So I just wanted to say that we're a little past the hour mark, so we're kind of burning into question time, which is fine. That's what this is meant to do. But so maybe if there's like any other concluding remarks you wanted to say, and then we can more formally give it over to questions.
Yeah. Since we have a lot of questions, I just want to go to one thing that I wanted to say. So this higher dimensional stuff, Dominik is going to talk about, so I'm just going to skip right over it. Okay, and I just want to mention evaporating black holes because that's really the our end goal was there. So now, we don't imagine some thermal equilibrium state. We imagine we had an SYK at some finite temperature, and we brought in like a 0 temperature wire. Okay, so the SYK is at finite temperature. We bring in a 0 temperature wire and just join it. Okay, and now this is a time dependent situation because the system will try to equilibrate, will try to thermalize and so on. So that is the thing that models an evaporating black hole, but the picture is very similar. So the orange curve here is some Cauchy slice. So this is the ADS boundary. On the left we have some ADS black hole. On the right we have this coupled heat path. This is the horizon. And the orange slice is a Cauchy slice. And again, we are trying to compute the entropy of this piece of the wire, okay? Because that's where the Hawking radiation goes. If the SYK emits some hot stuff into the wire, they will just end up in that faraway region, right? So computing the entropy of this blue region is like computing the entropy of Hawking radiation. That's why we've been going on about compute the entropy of the wire, compute the entropy of the wire, because it's really the entropy of the Hawking radiation that we want to compute. And again, at late times, past the page time, we have the causal wedge, which is here, but the entanglement wedge is bigger. It has this quantum extremal surface and it has this island. So this is like the island region. Okay, now I just want to conclude by mentioning there is a competition. So you might think, why did this new surface win, right? Why? So there is a surface 1, which is just the causal wedge. And there is a surface 2, which is causal plus this island, right? And okay, let's compare the generalized entropy in the two cases. In the island, you have this phi of A star term when you compute the S gen on the second surface, right? S gen on surface number 2 would be the old stuff plus phi of A star. Phi of A star is the area. So if the black hole is only like 60% evaporated, 40% of it is remaining, the area is huge, right? So you might think like, okay, I'm just creating a huge cost in the generalized entropy. Why is it beneficial to include this island? Like I have the causal wedge doesn't have this cost. It doesn't have an area term. Well, the point is the Hawking evaporation process has set up for us entangled pairs. So like Hawking radiation basically produces something like EPR pairs. One of them ends up inside and the other one ends up in this Hawking radiation, right? So here is sort of Alice and Bob in an EPR pair. And the point is, over the time evolution, over the lifetime of a black hole, we have had many, many of these pairs generated. So S gen of 1, if you just had the causal surface, you would have an entropy cost going like n log 2, right? Coming not from the area, but coming from the bulk entropy, right? So a generalized entropy, area plus bulk entropy. So if you just keep surface 1, just the causal wedge, you only capture half of the, you only capture one partner in each EPR pair. So you get penalized by the bulk entropy. In the surface 2, you included the EPR partners in your entanglement wedge. So those guys are no longer contributing to the bulk entropy term. And the only cost you have is A star. So basically you have a competition between n log 2 and this area. And the point is halfway evaporation is precisely the point when the area term starts to lose, like, it becomes small. The area becomes small, the entanglement is big. So it's actually better to go to surface number 2, right? Because there's a lot of entanglement. So you save on the entanglement, pay an area price. Okay, so that's the essential physics. It's again this EPR pairs that the Hawking radiation sort of produces. Okay.
I have a quick question.
Yes.
So how do you avoid the firewall problem?
Okay, let's maybe take that in the discussion thing. I just want to say that after you have this A star, the entropy, the generalized entropy on this A star is basically equal to the horizon area. This A star ends up very close to the horizon. And as the black hole is evaporating along this direction, its area is shrinking, right? It's just shrinking, shrinking, shrinking. And because the generalized entropy is essentially equal to the area of that horizon, it also shrinks. So you get something that goes up at early times and at late times switches over to this other entanglement wedge, which has this island and starts to go down. Okay. All right, so just the very final comment is that I don't want to say that we can compute everything in gravity using these pictures or using these islands. We thought before last year that even for getting this downward trend in the page curve, we would have needed, I don't know, some kind of resolution of the singularity or some information about string theory or what the UV of quantum gravity is. We didn't need that. We just needed to fix up this formula a little bit. We just needed to fix up the Ryutake-Yanagi formula a little bit. And then semi-classical techniques were enough to give us the von Neumann entropy. But the von Neumann entropy is just trace rho log rho, right? Rho is a big matrix. Trace rho log rho is a number. We didn't get the entire matrix, right, from these methods. The outstate of the Hawking radiation is some complicated thing, like it has a huge wave function. And trace rho log rho is just one number out of these like dim h whole squared numbers that make up the rho. And it would be interesting how much more just semi-classical gravity, like path integral over metrics, can tell us. I don't think it can go all the way to giving us all of rho ij, because then it would be moot to have a quantum theory of gravity. Like there's nothing more to compute. Rho ij is like everything in a black hole, right? So to compute each single individual matrix element, we probably need to know how the singularity gets resolved and so on and so forth. Well, we got a bit lucky in that we could compute this page curve, but we also got a bit unlucky in that the singularity played no role, and we would really like to understand the singularity better. Okay, thanks. I'll stop there.
All right, let's thank our speaker. Speaking craft. And now, so we have about 18 minutes of questions or so before 4:30 my time. And then we'll switch over to go to possibly the virtual chat in Perimeter. But for now, we have at least 20 more minutes of questions.
Let's go.
Hey, Raghu, I wanted to ask a question about including higher order corrections to the dileton. Like, so when you coupled your conformal matter to JT, you coupled it minimally, right? However, like if I take higher order corrections to the dileton from its extremal value, I could in principle include a dileton coupling to the conformal matter. And suppose I just repeat all the calculations which you did starting with this theory. Should I expect to see should I expect to reproduce all the results, or something should change?
I expect everything would be the same, because we also expect that in higher dimensions, the story is the same. Like Pennington in his first paper argued for this stuff happening even just in 4D Schwarzschild black holes, even though it's not a quantitative analysis, because the Hawking radiation and gray body effects and especially entropy computations are complicated. But these doubly holographic setups that Dominik will talk about, and also just general arguments that Pennington gave, it's basically very safe. Like at late times, this is the mechanism.
Yeah, so the reason I'm confused about this is that, like, I think the only thing which is universal from this dimensional reduction from higher dimension is the JT part, right? Because if you take the next order, which is like kind of the non-local action which Kitaev-Shu computed, those things are not universal. I think I don't know if I start from say Nordstrom or BTZ, I would get the same non-local correction.
Yeah. So I think maybe if you want to sort of go away from this kind of, if you want to do some quantitative computation, I think it's fair to try to do that. And I'm not like saying that that's a good exercise. Like we should understand this quantitatively in more complicated scenarios, but also just the place to try it would be just 4D Schwarzschild, right? Just the original space-time. And based on like general arguments, we know that such an island has to be there and whatever, but there's no quantitative things except in these doubly holographic setups. We do have some quantitative control.
So the generalized entropy should be universal, you're saying, even
well, the entropy formula doesn't have to be universal. What has to be universal is the fact that there is an extremal surface near the horizon of an evaporating black hole, right? The expression for the entropy is probably not universal.
I see.
Like the end result that there is such a surface is what was argued for in Pennington's paper.
Okay.
Yeah.
Right. And another question which I had was that, was it important for you to see this island? Was it important which CFT you coupled your SYK to? Like, you made some comment that your CFT has to be, the CFT, the wire which you coupled your SYK to was the same as the CFT matter which you added to JP.
Yeah.
Was that important in seeing this, or I could have coupled to some other?
No, you could have coupled to some other theory, but your boundary conditions would just be more complicated. Like you would have like some CFT on a half space coupled to some other CFT on the right half space. And then you would just have to specify some bunch of boundary conditions, how the fields of one go into the other, and so on and so forth. So
I see.
It would just make the computations a lot more complicated, but I don't think it would add new qualitative insights to the story.
Okay. Thanks.
Yeah.
Can I ask?
Yes.
Are you able to untangle for me a bit? Like, I have a tough time understanding what is due to rules which are being constructed in terms of rules to compute the entropy versus what exactly you're able to recover from the boundary and this wire in terms of, say, correlators or operators. Like,
sorry, could you say the question one more time? You're saying
it's a naive one because I just have a tough time understanding. You know, there seems to be a series of rules for relating the area and various definitions that are changing of entropy, and I'm not able to untangle kind of those rules.
Okay. Okay. So let me just say,
compared to just what you're actually able to recover from the boundary in terms of the correspondence.
Okay.
And
Yeah.
what the
Yeah.
duality,
okay. Let me just say,
like what part of the island are you able to actually recover from the boundary and the wire?
Well,
the SYK wire, for example.
Yeah. Yeah. So the short answer is you recover all of the island using the wire. But let me say what is being done. Just let's zoom out of all these computations, blah, blah, whatever. Like all you're trying to compute is you have some boundary theory, you're identifying a subsystem, and the only definition of entropy is trace rho log rho of that subsystem. That's all you're trying to compute. And you're also trying to ask, I have a subsystem on the boundary, what is the subsystem that it's dual to in the bulk? Those are the two questions. And the answer to that is just the entanglement wedge. Entanglement wedge computed using this Engelhardt-Wall formula, not the Ryuta-Yanagi formula, like the most, the most advanced version, the Engelhardt-Wall version. Okay, so that's it. Like so, you construct these functionals, you get the entanglement wedge, and then the entanglement wedge reconstruction is still the same statement that any operator in the entanglement wedge can be represented on that particular subsystem B on the boundary. That's all the same. The only thing that changed here was that the entanglement wedges became disconnected somehow. Right? That's the only new thing. Like otherwise, the story is the same. The only novelty is that you have these islands, which are some disconnected pieces of the entanglement wedge, which you might not have expected in the beginning. And they're crucial to solve these page curve type paradoxes. But reconstruction, entanglement wedge, Engelhardt-Wall, that's all just still the same from ADS-CFT from before, previous than last year. So just to sort of emphasize the thing before, if you have an excitation in this island region here, right? Let's say there is some guy who creates some kind of fuzz here, like creates some wave packet here. This operator will be represented on the dual description as some highly complicated non-local mess, but only in the relevant subsystem. Right? Or there exists a representation of this bulk excitation in the subregion which was responsible for creating it in the first place. And it doesn't matter if it's here, 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 whatever. All these would be reconstructed using the entanglement wedge, using modular flow, basically. And I should highlight here in this context, this very nice paper by Yiming Chen, who's a grad student at Princeton. It's a computation people should look at. He basically did this modular flow for free fermions in the bulk. And you just see it happening.
And I guess at the point where you get this island, if I'm near the boundary, then the operators there don't commute with these complicated operators that see inside the island. Is that this kind of?
Sorry, which operator doesn't commute?
Well, if I do say a local operator near the boundary.
Near the boundary here. This is the boundary. Sorry, can you see my? This is the boundary. This is not good. This thing is the boundary, right? So you are putting an operator here somewhere.
I guess I guess I was thinking the maybe this is for coffee, but I guess I was thinking the operators which are close to these to the complicated operator, which I think was near this wire that you were. I thought was near the wire that you were doing.
Okay, maybe let's talk.
Yes. Okay. Maybe that question doesn't make sense.
I have a
about
question.
it after getting the yes.
Yeah, so my question comes from a confusion of understanding this setup itself, where on the boundary there is this quantum mechanical system coupled to a wire, and in the bulk is this bath. The wire, you're saying, is the wire the same boundary that is there between the ADS2 and the bath?
Oh.
Just in that same figure that was there. Yeah, this boundary, the white line.
This line, the white line.
Yes.
It's just this, that is the time development of this point here.
Okay.
So the wire is like here. So this is the boundary, right? And then in time it just moves like vertically.
Okay, and another question is that I mean, I don't see why the wire which is a CFT would be dual to this subregion which is flat space in the bulk.
Well, the statement is that the combined system is dual to this picture.
Okay.
So it's this, it's important that there is some holographic system in the game, right? So we have this gravity system, this SYK, which is some holographic system, and it's coupled to this wire. And the coupled system is dual to this ADS plus flat space.
Okay, thanks.
Is that okay? Hope that was clear. Yeah.
So is there a simple way to understand why the quantum extremal surface appears close to the horizon after half the page time? Like, is it that we want to purify the radiation so that, I mean, is it that we want to purify the radiation that we choose this surface?
No, it's an output of a computation. It's not put in by hand. It's very important that you write the formulas, you get it out. So you see, that's the difference. Like earlier, people like Samir Mathur and various people have speculated this kind of thing. And back in the beginning of the firewall debate, people were saying things like A equals RB and ER equals EPR and stuff like that. But we didn't know exactly how much of the interior is encoded in this wire region, right? This A star, the location A star makes it quantitative. It's like it's here. It's this much of the interior, which is dual to this much of the wire. But yeah, this intuition was there from this, the fact that there is this so much entanglement and somehow that the degrees of freedom behind in the interior are just somehow encoded very non-locally in the radiation somehow.
Okay.
So.
Thank you.
I had a general question, Raghu.
Yes.
So it's not exactly related to the specific tutorial, but let me ask it anyway, and you can answer or not. So the comment you made about the semi-classical gravity actually able to answer the reproduction of page curve, which maybe one would have hoped that it would teach you something about actual quantum gravity, but it did not, right? The same way you said that trace.
Well, yeah, there's a qualifier, I'd say, but okay, go on.
But so in the same way that you said trace rho log rho is one number, but rho in principle is a much bigger matrix.
Yes.
I'm wondering, what are the other kind of questions one can maybe think about? So page curve is one example, but are there other questions like this? And have people thought, or have you guys thought about, will similar techniques answer them? Or at some point you say, this is where semi-classical gravity stops. You have to know something more than that.
Yeah, well, I think, for example, simple correlation functions can be computed.
Right.
Like this ZZ star quantity, like, okay, it's suitably averaged. So that's this whole work on the spectral form factor. If you suitably average it, then gravity, you can compute it reliably. And that extends to 2-point functions as well, like this work of Ilsad.
Okay.
And there was a recent paper, a single author paper by Douglas, Douglas Stanford, in which he was showing that gravity can reproduce some of like in some correlation functions.
Okay.
So, but if you ask for like S-point functions, where S is the entropy of the black hole, right? Then it probably doesn't get it right.
I see. So a correlation function of a large number of fields where it becomes comparable to.
Or even a 2-point function if you want to really get all the fine details of the energy spectrum, right? So if you write the 2-point function as a spectral decomposition as a sum of 2 energy eigenvalues, there are phases like either IT, En minus Em, right?
Right.
These phases produce a complicated beat pattern in the signal. Right. So the Ens is a complicated spectrum. Em is it's a double sum. There's a complicated beat pattern, and gravity doesn't know how to get that beat pattern. Like if you average it, if you smear out the wiggles, then you can get that signal, but you can't get sort of the actual beats,
So the smearing length scale somehow can tell you where semi-classical versus non-semi-classical gravity.
No, you have to smear it over a window which is much bigger than the e to the minus s, which is the separation between neighboring eigenvalues.
I see.
So if you bring it close or something like that, yeah. Right now, there is no hint, I think, of any kind of, well, up to some phenomenological models that people are working on, but yeah.
Mm-hmm. And what was the qualifier you said that there?
Well, the qualifier, I'm saying quantum gravity is, we should say what we mean. Like we can mean path integral over geometries, which is what basically all this work is doing. It's doing some path integral over G mu nu. Right. Okay, souped up to include wormholes and so on and so forth. But quantum gravity can also mean like string theory and strings and branes and all that UV completion. So, so there are these two kind of things.
Yeah, I understand. Okay, thanks.
Sorry.
Yes.
In the same sense that as this previous question, if I want to go ahead and compute like other Rayleigh entropies, what is technically stopping me from generalizing all these methods to? Because if I calculate all Rayleighs, it means that I have the full spectrum of the density matrix, right?
But the spectrum is not enough, right? The spectrum cannot tell you the overlap, the 2-point function of an arbitrary operator. You also need to know the matrix elements of the operators in the eigenvectors.
So that is where you're suggesting that the actual quantum gravity effects kick in, right?
Yeah, so I'm suggesting that the fine details of the correlation functions, which are encoded in the rho ij matrix, will need some ingredient from. That's my bias. Okay, I have no proof or whatever, but the only reason I say that is otherwise the singularity wouldn't need to be resolved if it didn't play any role whatsoever in any quantity then. So,
I see.
But I think there are some quantities which are special and you can go, you can compute it.
Thank you.
I'll just pause things here for a moment, and
Yes.
before we all thank Raghu, I'm just going to post into the chat there that there's a virtual coffee break spot that people can go to. You might have to log in, but you can you should be able to just use that link, and it's a bunch of tables, and you can just I encourage everyone to just plop yourself down at a table and introduce yourself, and people can chat there for about half an hour, and we'll reconvene at 5 p.m. UK time, and for Dominik's talk, and maybe we can all thank Raghu again for his really wonderful tutorial. Thanks very much.
Thanks a lot, guys. It was fun. Thank you.
Thanks.
And I do encourage people to also, if you're going to be back for the second tutorial, feel free to keep yourself logged in, if that's possible, just so we don't have to promote everyone to panelists again.